So we left off with the ionization of magnesium, and we saw that magnesium has two positive charges if it can dump two electrons from its outermost energy shell and just have its innermost energy cells then completely filled with electrons. Dumps two, it has two positive charges, and we call a positively charged ion like that a cation, and we would call magnesium then, if it has two positive charges on it by virtue of losing two electrons, we would call that a divalent cation, meaning two, divalent cation, and then it has two positive charges. So let's move on now and talk and treat a few other elements really quickly. Chlorine over here has 17 electrons. Note that we talked about argon having its valence shell completely filled at the third energy level for the s and p orbitals with 18 electrons. Chlorine is just missing one electron in that outer level. And so it would love to steal an electron from some other atom and thereby fill its outer valence shell. So chlorine has 17 protons, 17 neutrons, 17 electrons. And it's one short of having its third energy level completely filled with electrons. So if chlorine then gains an electron, pulls an electron off something else to fill its valence shell, then it has 18 electrons. It still has 17 protons and 17 neutrons, but it has 18 electrons, and therefore it becomes negatively charged. And that is a monovalent anion. That's an anion because it's negatively charged. So if we come over here to sodium, you see that sodium's a lot like magnesium, except it has one fewer electron. Sodium only has to give up one electron to dump it, to basically clear its outermost energy level and just go to the first and second energy levels. You can configure that yourself if you want to. Go ahead and draw a nucleus and draw your energy levels and see that that is true for sodium. So sodium can dump an electron. So it dumps an electron, and it then has a single positive charge on it because it has one more proton than it does electrons when it does that. And we'll look at this in a minute. We'll look at sodium chloride, table salt, and talk about the way that table salt actually bonds. So now we're ready to tackle the nature of different types of chemical bonds, at least a few of them, and that's where we're going to go next. So turning now to chemical bonds, generally speaking, we can say that molecules are groups of atoms that are held together in some type of stable association. And that stability can be achieved by a number of different types of bonding situations that we'll talk about a few of them here. Now, when we talk about compounds, they are molecules. A molecule is two or more atoms that are linked together. But compounds are molecules that contain more than one type of element. So an example of something that's not a compound would be molecular oxygen, say, because that is composed of one type of element. Molecular oxygen is a molecule because it is two atoms of oxygen bonded together, but it is not a compound. So whereas, let's say, CO2, carbon dioxide, is a compound because it has both the element carbon in it and the element oxygen in it. So whenever you have two or more elements in some molecule, then that molecule we can refer to as a compound. And atoms are held together in molecules or compounds by bonds, as I've already said, and we'll talk about some of those. So we've already talked about covalent bonds, and just quickly reviewing, they form when atoms share two or more of their valence or outer shell electrons. Covalent bonds result in no net full charge, and they strive to satisfy an octet rule so that there are no unpaired electrons. So bonding of atoms together achieves the desirable thermodynamic result that there are no or very few unpaired electrons. And the strength of a covalent bond depends on the number of the shared electrons. I've already mentioned that CO2 has 2 double bonds in it. And those double bonds are stronger than a single bond would be because there are 2 shared electrons between the 2 atoms here and 2 there. So 2 pairs of shared electrons in a double bond, each single bond being 1 pair of shared electrons. A double bond is much stronger than a single bond. And likewise, a triple bond, say, 2 nitrogens triple bonded with each other, that triple bond is even stronger. So in biology, in biological compounds, many compounds are composed of more than 2 atoms. And you can have sharing electrons with 2 or more atoms can share electrons. So we'll talk about that, especially when we get to protein structure. So we've just reviewing here, H2 here. If we have hydrogen gas, H2, hydrogen has 1 proton in its nucleus and 1 electron in its 1s orbital. 2 hydrogen atoms can achieve a filling of the 1s orbital at the first energy level by sharing a pair of electrons. So that's H2 is covalently bonded, 2 hydrogen atoms covalently bonded. Here, O2, as we've talked about, double bonds, a pair of double bonds, 2 oxygens are linked together. They share 2 pairs of electrons in a double bond. And nitrogen, as I've already mentioned, can have a nitrogen gas, and 2 would be triple bonded 2 nitrogens together. And there are 3 pairs then of shared electrons between nitrogen atoms. And you could, if you wanted to, you could just work out the configuration for nitrogen singly, and then another one singly, and then look at how they might share their valence electrons so as to satisfy the octet rule. I would recommend doing that. So ionic bonds are not covalent bonds. So this is a different type of bond that we're going to be talking about, ionic bonds. And they are formed by the attraction of oppositely charged ions. So we talked about how sodium can lose an electron and become a monovalent cation. We've talked about how chlorine can gain an electron to become a monovalent anion, and therefore sodium and chloride can remain associated as an ionic compound, attracted by or held together by the attraction of oppositely charged ions. So that's what ionic bonds are. They're not shared electrons. They're not like a covalent bond. They're not shared electrons. Rather, they are electrostatic attractions between positively and negatively charged ions. And water molecule, being a polar molecule, as we will see, it can disrupt the holding of those ions together and thereby solubilize a salt that would be sodium chloride linked together by ionic bonds. So let's look at that real quickly. Here we have a sodium atom which would like to get rid of an electron so as to have a completely filled outer electron shell at the second energy level. It would have no electrons then at its third energy level. It would like to get rid of an electron, and chlorine would love to grab that electron and thereby satisfy its octet rule for its third energy level. And when that happens, of course, chloride gains an electron, so it becomes negatively charged. Sodium loses an electron, so it becomes positively charged. And sodium and chlorine then can be held together in a crystal of interacting positively charged sodiums and negatively charged chlorines. And these atoms are held together by ionic bonds, by electrostatic attractions, not the sharing of electrons. Simply positive charges being drawn to negative charges, and negative charges being drawn to positive charges. And this would form a sodium table salt crystal. Now, one thing we should mention is that the phenomenon of redox, reduction and oxidation. Redox stands for reduction and oxidation. And we mentioned previously that oxidation is the loss of an electron, and reduction is the gain of an electron. So when an atom gains an electron from another atom, we say that atom is reduced. Whereas if one atom loses an electron to another atom, then that atom is oxidized. And this will become very important when we talk about electron transfer in the flow of energy in both photosynthesis and in metabolism. So keep that in mind. Now, there's a phenomenon called electronegativity, in that atoms do not all have the same affinity for electrons. So electronegativity refers to the strength by which an electron can be held by a particular atom. Now, when we have covalent bonds, we can have two atoms, say, in a single covalent bond. Let's imagine they're sharing a pair of electrons. Those electrons can be shared equally between the two participating atoms. But if there's a large difference in electronegativity of the two participating atoms, then you can end up with a polar covalent bond. So, for example, if we take the case of water, which we're going to get to in a minute, hydrogen is bonded to oxygen, and another hydrogen is bonded to oxygen. So oxygen and hydrogen here share a pair of electrons, and oxygen and hydrogen there share a pair of electrons. Hydrogen wants to form one bond. This one does too. Oxygen wants to form two bonds. Well, oxygen has a much greater electronegativity than hydrogen. And so oxygen ends up with what we would say a partial negative charge, because it holds the electrons that it's sharing with hydrogen more tightly than hydrogen does. And likewise, hydrogens end up with a partial positive charge on them. I'm indicating partial with this little sigma sign here. So the water is an example of polar covalent bonds, because there's an unequal sharing of electrons. You can think of it that the electrons spend more time around oxygen than they do around hydrogen. So the shared electrons are spending more time around oxygen, imparting a partial negative charge to the oxygen, and the hydrogens acquiring partial positive charges as a result. And so an example of a nonpolar covalent bond would be carbon and hydrogen. So if we look at, for example, methane, carbon bonded to 4 hydrogens. Carbon and hydrogen have roughly equivalent electronegativity values, and therefore carbon does not hold the shared electrons more tightly than any of these hydrogens. And you don't find any of the partial charges that we found with water. We don't find those with a non-polar covalently bonded situation as we have here. So next we'll look at some electronegativity values for some common atoms, and then move on to the special properties of water that make it essential for life on Earth as we know it.